So lung volumes. This one's a little bit self-explanatory, so you could just go ahead to maybe physiological dead space, which is also in this lecture, is a little more useful. But basically, we're going to talk about different types of lung volumes. First of all, I want to define something. Capacity is a term for a sum of two lung volumes. So we're going to see what that means in a second. But first of all, I want to focus on this lung volume. This is a tidal volume. This is the volume of air that you take in with a normal inspiration. Okay, so you run out of air you need to inspire. You do a normal inspiration, you take in around 500 milliliters of air. Okay, that is your tidal volume. Next is the inspiratory reserve volume. So this is a normal inspiration, right? But the inspiratory reserve volume, what does that mean? It's the reserve. So how much more inspiration you could do after a normal inspiration. So that's what it is. It's exactly this. How much more air you could breathe in after a normal inspiration. Tidal volume we talked about. Expiratory reserve volume is the same idea. It's the reserve that you could do after a normal expiration. So you take in after, and then after you've normally expired. How much more air could you push out of your lungs if you really tried to? So you could try that right now and you just think about it. So you can do a normal breath, and you realize that you can actually push out quite a bit more air even after a normal breath, and that would be your expiratory reserve volume. Finally, you have your residual volume. This is going to be amount of air left in your lungs after a maximal expiration, okay? So even if you push as hard as you can, there's going to be some air left in your lung. This is called the residual volume. Note that you can't measure this value through spirometry. Now I tell you again, a capacity is a term for a sum of two or more lung volumes. So the ones we just talked about now were lung volumes, so now we're going to talk about capacities, okay? Inspiratory capacity. This is the maximum amount of air you can breathe in after a normal exhalation. So you expire normally, and then now if you breathe in as much as you can, that's your inspiratory capacity. Your capacity to inspire after a normal exhalation. Next is the functional reserve capacity. Okay, this is the amount of air in your lungs after a normal exhalation. Finally, vital capacity. This is the maximum amount of gas that you can inspire or even exhale, either one. If you push out as much as you can, if you take as deep a breath as you can, and push out as much as you can, that's the volume of air that's your vital capacity, okay? So you can just if you can memorize it, remember it easy. If you don't, then if you can know the volumes, the rest is easy, because again, it's like stepwise. Then inspiratory capacity is just the top two together, and then functional reserve capacity is the bottom two, and then vital capacity is pretty much all of them except for residual volume. Okay, so total lung capacity is basically the maximum possible volume of gas in the lungs. Now we're going to talk about dead space. First is physiological dead space, or first is anatomical dead space, excuse me. This is the volume of air in the respiratory tract that does not reach the alveoli for gas exchange. So remember what I said, in a normal normal breath, we take in about 500 milliliters of air. About 150 milliliters of that does not reach the alveoli. Okay, and where does it go? Remember that this is our respiratory tree. This stuff is all conducting zone, as you can see here. So air can still stay here, it can stay in the trachea, it can be in the bronchi, it can be in the bronchioles, terminal bronchioles. None of that is going to be participating in gas exchange. So 150 milliliters of that air is going to be in all this stuff. It's not participating in gas exchange, it's just hanging out in your respiratory tree, okay? And that is called the anatomical dead space, because it's dead space because they're not really being used for gas exchange. It's all wasted. Next is physiological dead space. This is the total volume of air in the lungs that does not participate in gas exchange. So what's the difference between this and anatomical dead space? Well, basically, there's air also in the alveoli that could also not be in contact with blood for gas exchange. Normally, this doesn't happen normally. But if you have pathology, if you have disease with problems, then you can have air in alveoli that's not being involved in gas exchange. Maybe there's no blood going to that alveoli or something. So that would be physiological dead space. That's the anatomical dead space plus the dead space inside the alveoli. That's physiological dead space. And we can actually calculate this. Physiological dead space equals to this. This is tidal volume times this. This is the the arterial partial pressure partial pressure of carbon dioxide in the pulmonary arterioles minus the expired partial pressure of CO2 in expired air. Okay, you divide that by the partial pressure of CO2 in the arterioles. Okay, you can just easily memorize this. Just remember taco paco, and the reason why is because it's it's the pulmonary arterial minus, you just don't know, is it pulmonary arterial or is this one first, or is it the expired CO2 first? And taco paco helps you remember that. It's tidal volume times paco, so paco is this one, so this one's first. If you want to understand why this equation works, let's consider this. Consider a case where the partial pressure of CO2 in the arterioles is the same as in the expired air. If they are the same, what happens? That means that you have a complete gas exchange. There was no wasted ventilation at all. And if they're the same, then this will equal to 0, right? So 0 times VT equals to 0. That means your physiological dead space was 0. And it makes total sense. If you had no wasted gas exchange, your physiological dead space was 0. If you consider the other case, in which case there was 0 expired CO2, what would happen? If you had 0 expired CO2, then you're basically, knock this out. This becomes 1. So physiological dead space equals to tidal volume. That means all of the air you breathe in nothing was involved in gas exchange. And that makes sense, because then obviously none of the CO2 in the arteries were able to make it out into the alveoli and thus into the expired air. In that case, your physiological dead space is all the air that you breathe in. That's the tidal volume. So, otherwise, just remember taco paco. Honestly, it's easy. Now, note in general, this is going to be important to remember this, but it's more just because we'll see this over and over again. When we use a big A, we mean alveoli. Okay, little a, we mean arterioles. So this would mean alveolar oxygen partial pressure. This means arterial oxygen partial pressure. I emphasize that we're going to see something called an AA gradient. We're going to see stuff all over. So AA gradient is like the gradient of oxygen in the alveoli versus in the arterioles. Things like that. We're going to see it over and over again. So just remember, big A for alveoli, small a for arterioles. Finally, really basic stuff. You can skip ahead, just read ahead. Minute ventilation. This is the volume of gas entering the lungs each minute. And the way you calculate this is you do tidal volume, so the volume of gas with each breath, and respiratory rate, how many breaths you're taking in a minute. You multiply those, you get the volume of gas entering the lung each minute, aka minute ventilation. Now, alveolar ventilation, this is the volume of gas available for gas exchange at the alveoli each minute. So, how do we know the volume of gas available for gas exchange? Well, we take the tidal volume, which is all the gas we take in, and we subtract the physiological dead space. That's the amount of air, the volume of air that's not being available for gas exchange. Okay, so that's the volume of gas available for gas exchange. And then you multiply that by the respiratory rate, and then you get alveolar ventilation. Finally, thing to note is normal respiratory rate is between 12 to 20 breaths per minute. Okay, so that's it for our little overview of lung volumes, physiological dead space, and ventilation.